Does this list look familiar? These are numbers we know about, right? We gave them labels. What are all these guys up here? This one actually should be here, shouldn't it? Sorry. These guys are the counting numbers, or the natural numbers, right? Okay? What are these ones? These are, so they're inclusive of the natural numbers, you get the integers, right? These guys, okay? I suppose you could say z minus, but if I include all of those, it's just z, okay? What about these guys? What are they called? They're called rationals, right? Rationals? Okay? How about these guys in here? These are actually also in this same camp, right? They're just written a bit differently. Okay, what do you call these? Now you could call them irrational, but if you just consider all of these together, right? You remember we did the Venn diagram and expanded? These guys are real. And then that leaves us with, so I'm imagining, or if I added other numbers, you get the complex numbers. Alright, now, get this, okay? All of these numbers together, and I think we had phi in there somewhere as well. Where would phi go? Where would phi fit? Is phi a natural number? No. Is it an integer? No. It's not rational, is it? It'd be in here, wouldn't it? I think phi would be here. All of these numbers, believe it or not, are all actually part of one big family. And here's your heading for today. All of these numbers are called the algebraic numbers. The algebraic numbers. So this is a bit like, if you want to think like, if you want to think of biology, right? You know how there's like species, and then there's, what's above a species? A genus? Genus? Is there anything above a genus? What's above a genus? Families, okay? And you're like, it's like me and like, you know, jellyfish. What do we have in common? It's like, well, we're carbon-based or whatever. All of these things, they have in common this. Now, why do you think they're called, like, we get why rational numbers are called rational numbers. Even to an extent we get why natural numbers are called that. Why are they called algebraic numbers? Yeah, Brendan. Okay, because all of these numbers, like when you were creating your expressions, what you were really, I didn't tell you this, but you were creating equations, right? All of these algebraic numbers you got, they're all solutions. I don't know what that's this one, but you know, they're all solutions to these equations. And these are algebraic equations. We use the tools of algebra, right? And when you solve every one of these, you'll get an algebraic number. Okay? Now here's the weird, funky thing. There are numbers that don't belong to this set. Okay, and this is feeding into our next topic of math error and things that is math discovered? That was our big debate point. By the way, I really loved reading all of the disagreement and anger and no, you're wrong of the discussions over the weekend. Right? There are numbers that don't belong here. Right? That these numbers are what we've invented. Right? This is what I put to you. Okay? They have been created and formed and found through invented means. But there are numbers that aren't in here, and I'm going to give you two. Actually, you kind of know what they are. Okay? The first one is the little absence from here, right? What's the big superstar number of mathematics? It's pi. It's pi. Now, just consider this with me for a second. Where does pi come from? Where does it come from? Where does it come from? Yeah, Nikita. Good. Very close. It's about the circumference versus the diameter, right? So it's a very simple shape. It's a very simple shape, but you guys know we're into thinking deeply about simple things, right? So this number comes out of this, and guess what? You can't build it any way using algebra. It's impossible, right? In fact, to put it this way, pi is not the solution. Sorry, that's an abbreviation. I just ran out of space. To any polynomial equation. That's the fancy way of saying it. Right? You can write any polynomial you like. You guys have seen polynomials before. You know, you got squares, you've got plus, minus, fours, whatever you like, right? There's no polynomial you can write where pi will be one of the solutions, or one of the roots if you were drawing it, that kind of thing. Okay. Now we know what pi is. The other one, and I sort of mentioned it very briefly, is e. Okay. Now if you have your calculator there, you can get e. And yeah, we have talked about this briefly in passing before. 2.7182. Here's how we're going to do it. I'll show you how we get it, and then you'll see how it's, well, maybe you'll be able to work out why it's e. Okay. Put your pens down for a second. Put your pens down. I'm going to give you a metaphor, right? And then it'll get us to this number, this strange number, okay? I'm going to take you to the bank. Take you to the bank, okay? Now, if you go to the bank, okay, and you say, well, I'm going to invest some money, you're going to get interest back for your money, right? Now, I know we talk about simple and compound interest, but simple interest, no one really pays simple interest. So, compound interest. What is, sorry, that should be an A. What is the compound interest formula? It's P, right, times 1 plus R to the N. Okay, now what are the pieces? P for principal, the amount of money you put in there. R for rate, like percentage. N for, yeah, number of years, months, whatever. Okay. Now, compounding periods. Now, so far, so good. We're still using algebraic tools. Okay. Now, I hope you see, the amount that you put in there doesn't matter all that much. It's not that important to what's going on. You can put in $1,000, $5,000. I'm just going to imagine, what if you just put in $1? Okay? The reason why is, I don't know if you, let's do a bit of an experiment, okay? Suppose you have $5,000. Which do you think is better? Putting it in one bank account with $5,000, or putting it in 5,000 bank accounts, each with $1 in them. Which one is better? Now, it's kind of funny. Assuming they have the same, think of the fees. Assuming no fees, same interest rate. Actually, there's no difference. You can go ahead and prove it for yourself if you like. You can use this formula, it's not that hard. But for that reason, I'm just going to consider $1. Because then if you got more than $1, it's no big deal. Alright, now, let's suppose it's a really generous place. Really, really, really generous. Okay? And it gives you an interest rate of 100%. Oh my god. Very, very generous. Okay? So, this bank is run by someone with very, very deep pockets, like, say me. Okay, obviously not, right? Wouldn't be run by me, but suppose. Okay? Now here's the thing, right? If we put it in for, say, a year, right? Then that'd be, 1. But actually, you guys know, it actually doesn't sit there for a whole year and then double, right? In fact, our banks, they give you interest a little more frequently than that. How often? They'll pay you every month, but they actually calculate it every single day. Did you know that? Now, if you've got e-banking, you can go and log on and you can see it's like, oh cool, I earned 3.2 cents today, or something trivial like that. But that's what happens. Now, being that, each day you're actually getting one little fraction of the interest. This number changes, doesn't it? Right? This number changes. It's going to be the compound interest, which is 365. Okay. So therefore, now you have a calculator there. How much will you have at the end of the year? No, seriously, how much will you have? Go and work out, you've got a calculator there. So it's 100%, right? It's just 1.
1 plus 1 plus 1.
Yeah, like what?
Whoa, what did you get? 2 point. Okay, now hold on a second. You're like, huh? That's a bit funny. But wait a second. If I didn't do it frequently, if I didn't do it every day, if you just at the end of the year you just get double, right? Or if you do it every day, you get more. What if you did it more frequently? What if you did it, say, there's 24 hours in a day, right? So every hour, let's do it every hour, right? Which means that this is going to be times 24, right? So you won't get 2.714567 anymore, will you? What do you get?
A greater.
You get more, right? But how much?
Is that the most?
What do you get? What do you get? Come on, give me some decimal places.
Oh, you get
Yeah, Lewis.
71812.
812. You're like, no, more. Come on. How about not every hour? How about every minute?
Is that the most?
What do you get? What do you get? I can tell you now. You're probably going to get 2, 8, something like that. Okay. In fact, what you're going to get is this sucker. Okay. Now, what have we just done? What have we just done? Shh. What we are modeling right now is something that grows, and as it gets bigger, right, it grows faster. Does that make sense? Because, you know, the more money that's in there, the more interest it earns. That's the way compound interest works. If I drew it, it would look like this. Starting off at $1. Yeah, it's an E for exponential curve, right? This number, this is the number of exponential growth everywhere in the universe. And you can't build it like this. We sort of did, right? Yeah. But what you really need to do, like, these things won't give you this exact number, right? You have to keep on doing it, and you have to keep on doing it forever, okay? So these two guys, they're the big important numbers in maths, okay? Now, ready for me to, this is just a side note, just a little thing to freak you out a little bit. These numbers, they're not just randomly connected and cool, right? If you take E, right, unfortunately your calculators can't do this unless you have a, I think if you have an FX100 you might. But if you raise it to the power of pi, you'd expect that to be a weird number, right? Or if you raise it to the power of I times pi, you get that.
So I don't have an I.
Yeah, you probably don't have I in your calculator.
Why don't you just say root -1?
Math error.
It'll spit you back a math error. It won't do it. So what's this about? These are weird numbers. So in summary, you've got all these over here. These are what we call the algebraic numbers. The numbers we can build with our tools. These numbers over here, they come from somewhere else. We didn't make these things. We didn't design this. This is everywhere in the universe. It transcends the tools that we have for building numbers, which is why they're called transcendental numbers. Let me say that again. Okay? You got all these numbers over here, this huge family of numbers that we can build through algebra. And then you've got these weird guys, who they are real, obviously. Well, not this kind of real. They're some kind of number, but they transcend the tools that we have for building numbers. They're transcendental numbers. Okay. Now, they're not the only ones in pi, but they're the most famous ones.